11. This is Dr. Beck with another one of our physics videos. For this you will need your book and you will also need your booklet. For now, however, here is our do now task. So in the back of your book, without using your notes, can you please spend the next 5 minutes answering these questions? Please now pause the video and attempt these. Okay, welcome back. So the first one is one we've seen before. Define the word force. Really importantly, you understand this and can reproduce this. A force is an attractive or repulsive interaction between two objects. Each part of that definition is really important. Second, we get confused with our units. We have here millimeters. How many millimeters are there in 2.5 or 2.5 meters? Well, first of all, how many millimeters are there in 1 meter? A millimeter is a thousandth of a meter. So 1,000 millimeters is the same as or equal to 1 meter. Here's the abbreviation for millimeter. Always a lowercase m, please. So, okay, if we've got 2,000 millimeters, we've got 2 meters. So 2.5 will simply be 1,000 times 2.5, which equals 2,500 millimeters. Again, check if your answer makes sense. A millimeter is that tiny part of your ruler. It must be a lot bigger than that. A lot bigger than that. So this answer makes sense and is correct. What is the equation that links these three things together? Again, we've had this before. We can simply write it down, at least perhaps in a margin of an exam, W equals mg, but then we have to write it out in full. The weight of an object is given by its mass multiplied by the local gravitational field strength. This is the best way to write it. If you rearrange that, then please be really careful how you do that. Next, sketch these and label the resultant forces. So these are free body diagrams showing forces acting on any object. The rule is we take the smaller force away from the larger force if those things are acting in opposite directions. And then we add our arrow in the direction of the larger force, and that will therefore show us the resultant force. So they are acting in opposite directions, not just different, opposite. So here we have 75 to the right and 50 to the left. We'll take the 75 to the right being positive. So plus 75, take away 50, and it will be in this positive direction. Remember, a force is a vector quantity. So this will be 25 newtons. This one is slightly different. Here the forces are acting in the same direction. So again, we will define this as being our positive direction. This time they're both acting to the right. So we simply now add these. So long as we then label the arrow, we will get the mark. Finally, a little bit more difficult, but these are now not acting in opposite directions, they are acting in different directions. So we are going to need to construct our parallel of forces, parallelogram of forces. Now, as it happens, I've chosen these numbers and this right angle. This is actually a 5, 12, 13 triangle. You can actually work it out. Or if you draw an accurate diagram, you can measure it. So if you draw this on graph paper and you have a suitable scale, you can actually measure the lengths of these sides in centimeters, then convert using the scale. As it happens, I know that 5 squared plus 12 squared gives us 13 squared. So this length is 13 units, and because it's a force, we're going to add the unit Newton. Okay, so I'll just complete the arrow to make it a more accurate diagram. 13 newtons. So well then, if you got all those right, let's have a look at today's lesson. Okay, so today then, in the fronts of our books, can we please make a note of today's lesson and its objectives, and also, as always, our scientific keywords. I'll give you some minutes to do that. When you're ready, you can come back to the video. For now though, please just pause. Okay, brilliant. So we're going to be today looking at Newton's second law of motion, or simply Newton's second law. We're going to be looking in particular at force and acceleration. We're going to learn what happens when a resultant force acts on an object, so that I can use the equation for Newton's second law of motion. Now, all that sounds quite scary. It actually isn't. We're just basically going to do a little bit of maths. But first of all, we need to understand what it is we're doing. Along the way, we are going to be using, as always, these key words. We have 6 up there: force, acceleration, vector, speed, velocity, and mass. Here's a picture of a skydiver falling in free fall from an aeroplane or some other object. And here's a statement. Let's unpick this statement. It says, if an object is acted on by a resultant force, it will accelerate in the direction in which the force is acting. Lots to think about there. Let's draw a free body diagram of our skydiver. There he is, or she is. This skydiver could be experiencing a downward force, or will be experiencing a downward force, and we will call this his or her weight. Now, as he or she is falling, they will experience an upwards force, and that will be due to air resistance. This is a contact force. For air resistance to have an effect, you need to be in contact with the air particles, and they will push against anything which is falling or moving through the air. Now, this diagram suggests that the upwards arrow is the same length as the downwards arrow. So here we would say that the overall resultant force equals 0, or 0 newtons. If these arrows are the same length, and I've drawn them deliberately so they appear to be, that would be 0 newtons resultant force. If, however, we change this slightly, and let's say at the start of their journey, the air resistance is much smaller. Their weight will remain the same. They still have the same mass. They're still falling towards the Earth and experiencing gravity. That will produce their weight. That won't change. But now we can see these arrows down and up are different lengths. So here there will be a resultant force. Now, as we saw with our starter task, we can calculate that if we had numbers. We don't have numbers here. However, we can see there will be a resultant force down towards the ground. Let's have a look what this means. If an object is acted on by a resultant force, it will accelerate in the direction in which the force is acting. Okay, so here we go. Here's our free body diagram. We have a resultant force downwards. We could redraw this resultant force as a simplified resultant force diagram. So here we go. This is our simplified resultant force on a free body diagram. This person, this thing, this object will be then accelerating downwards. Not just moving down, they will be accelerating downwards. What does that mean? Well, they will be getting faster. They will be accelerating in the direction which the force is acting. There is a resultant force down. They will be accelerating down, not just falling down. If the person were experiencing no resultant force, and these forces were balanced, then they wouldn't just stop. these forces might be balanced and the resultant force might well be zero. In fact, it is. What that doesn't mean is they will stop. It just will mean they stop accelerating. So they will then be moving at a constant speed. They will not be accelerating. Now we'll use another word for speed in a second, but for the moment this is fine. A constant speed. If there is zero resultant force. If there is a resultant force, and here's our free body diagram showing that, that is a resultant force, they will be accelerating in the direction of that resultant force. It isn't enough to say moving, accelerating. And this is something called Newton's second law of motion. Newton's second law, if we turn to page 19, the resultant force on an object which is free to move, i.e. a skydiver moving through the air, if it's free to move, it will cause the object to accelerate. Now, what does that word mean? We've mentioned it a few times. Well, we might use that word in everyday language. Acceleration is a change in velocity. That's an interesting word. Do we know what this word means? Acceleration is a change in velocity. Velocity is related to speed. Okay, it can be a change, it can be an increase or a decrease. Velocity and acceleration actually doesn't mean it's going to get it faster. In physics, acceleration just means a change. Okay, and that's something we can get our head around. Acceleration is a change in velocity. So let's consider what we mean by speed and velocity. Now, first of all, speed is something we call a scalar quantity. What we mean by this is it just needs to have a size. So if we're moving 2 meters every second, we will say that we are moving at a speed of 2 meters per second. Using the old units, let's say a car is moving at 30 miles per hour. Okay. Now, notice here it's fine. That's everyday use of language. However, what we don't have here is a vector quantity, and the vector quantity is velocity. As you've already seen, a vector quantity must have both size and direction. Okay. So, if we're moving at 2 meters per second to the right, that would suggest a velocity because we have our speed, 2 meters per second, therefore the size, but we also have our vector quantity. Now this is where it gets a little bit weird, just bear with me. So we can say we are moving 2 meters per second to the right. So let's have our scale. I'm going to put a 0 in the middle here. 2 meters per second to the right. On our scale, that's over here somewhere. So 2 meters per second to the right. So that's our positive direction. So this will be 2 meters per second. Same units as before, 2 meters per second. Let's see what happens if I now move to the left. Using this idea, if I move to the left, I'm going backwards. I'm going in a negative direction. I've said that to the right is positive. If I move to the left, I'm going in a negative direction. A negative is part of this vector quantity. I'm therefore moving relative to my starting position minus 2 meters per second. Wow. 2 meters per second to the right is 2 meters per second. 2 meters per second to the left is minus 2 meters per second. This minus tells us the direction. Now, weirdly, this is the same as 2 meters per second speed, because we're moving at 2 meters per second. This doesn't need the direction. The speed does not need direction. But anyway, velocity is the speed of an object in a particular direction. Okay, so velocity is the speed of an object. We can interchange it with speed for now, but this will become more and more important as we move through the module. Okay. So acceleration then is a change in velocity. We can link it to a change in speed. It could be an increase or a decrease in speed. Now, because it's a change in velocity, it could also be a change in direction. Also be a change in direction, because the change in direction would affect the velocity. What we now have then is this idea of Newton's second law. If we apply a force to an object, it will accelerate. Its velocity will change. However, the larger the mass of an object, the more difficult it is to get it to change its velocity. Again, this kind of makes sense. Remember, we're going to change something's velocity, change something's speed in a particular direction. If I'm trying to push a huge rock, to accelerate it, I'm going to need to apply much more force than if I'm trying to move a small pebble. It makes sense. A larger force is needed to accelerate a larger object, a larger mass object. And this is the relationship. So after all this simply is Newton's second law in equation form. And we usually summarize it like this. The force is the mass of the object multiplied by the acceleration. Now we know that the force is measured in newtons. We know, or we should know, that the mass of an object is measured in kilograms, not grams or anything else. And the acceleration, just like speed, will be measured in meters per second, but we're changing the speed. We measure this in meters per second per second. The change in speed per second. Sometimes then we summarize that as meters per second squared. So this is a little bit more complicated, but ultimately it's about numbers. So long as we have the right units, we don't need to worry about the numbers. We don't need to worry about the units. If we have the right units, they're fine. We just have to deal with the numbers. So we have our force always as our base unit in newtons. The mass, our base unit, is always kilograms, and the acceleration is always measured in these units of meters per second squared. Again, if you want to pause the video or go back and track through what I've just been saying, feel free, you can do that and move on. Here then is what we've come so far. Okay, so I've just rewrote this. This is taken from a textbook. We have the resultant force, F, not just general force, a resultant force. If there's no force on an object, resultant force, then there will be no change in velocity. So if there is a resultant force, it will produce an acceleration. How much acceleration depends on the object's mass. Acceleration is proportional to the resultant force and inversely proportional to the mass of the object. For the same force, a big mass will accelerate less than a small mass which will accelerate more. That's inversely proportional. Okay, we're going to do some numeracy tasks. Again, this is about as difficult as it gets. All we need to do is check the units. We remember our equation, F equals m times a, or simply F equals ma. So we're going to go through a few. I'm going to go through a few. And then you're going to have a go by yourself. So let's do our first equation, our first calculation. Here we have two things we know about an object. The mass is 12 kilograms and the acceleration is 25 meters per second squared. First thing we do is we check we're using the right units. Kilograms is our standard unit. That's good to go. The acceleration is in our standard units. That's also good to go. So F equals m times a. Force is mass times acceleration. The force, therefore, is simply 12 multiplied by 25. Okay, so the number comes out as 300. And we recall that any force is measured in the units of newtons. So there's our first answer. Let's have a look at the next one. It is number 4 because of the way the questions are sorted out or set out, but let's have a look at this slightly different one. Now let's start with our equation this time. Let's see what we know. Acceleration is 7.9 meters per second. That's good. That's the correct unit. And the force this time is in the correct unit. But this time, we're asked to work out the mass. Right, so we need to then rearrange this. I'm going to divide both sides of this equation by the acceleration. So F divided by A equals m times A divided by A. All right, great. Anything divided by itself just gives me 1. So m times 1 will be F over A. M equals F over A. Our numbers are right, our units are right, so the mass is 91 divided by 7.9, and that gives us an answer of 11.5. Let's check our units. This is the mass in standard unit. We have then the kilogram, 11.5 kilograms. Let's do one more and we can then continue. So let's just start once again with our equation, F equals ma, or F equals m times a. Let's just check our units. We've got a problem here. We've not got newtons, we've got kilonewtons. 1 kilonewton, 1 kilo anything, is 1,000 of those things. So 1,000 newtons. So here we have got not just 1,000 newtons, we have got 13,000 newtons. So a huge force, massive force. I'm going to expect this to produce a big acceleration. Let's see if our answer is going to make sense. We've got a huge force acting on a reasonable mass, perhaps the size of a young adult. However, this time we're asked to work out the acceleration. I'm going to divide both of these sides by m. Again, I find that anything divided by itself gives us 1. A equals F divided by m. Just rearranging that equation. So the acceleration, the force, don't forget, the force was huge. The force was 13 kilonewtons, 13,000 divided by 58. 13,000 divided by 58 gives us an answer of 224.1. I'll leave it at 1 decimal point. And the units, now the units, remember, meters per second, we can write that as meters per second squared. Okay, so we've done that in 3 different ways. We've been really careful about our units, but we've also rearranged the equation. So let's have a look then at our task for the remainder of this part of the lesson. I've done question 1, I've done question 4, and I've done question 7. I'm going to give you 15 minutes to have a go at the remainder of those questions. So in your book, please write the question number. Please show you're working out, and then don't forget to check your unit at the end of your calculation. 15 minutes, please pause the video. Okay, welcome back. Hope you didn't find those too challenging. There were a few things in there to look out for. Let's start with number 2. Okay, as always, I like to start with the equation F equals m times a. Now, as it happens, we're being asked to find out the force, so we don't need the equation to be rearranged. However, hopefully some of you noticed that this is not our standard unit. There are 1,000 grams in 1 kilogram, so we have to divide this. 100 divided by 1,000. So whatever we end up with is going to be less than 1 kilogram. This will be 0.1 kilograms. The acceleration is fine, that's in the right units, so we simply plug these numbers into our equation, and we have the mass of 0.1 multiplied by 6.3, and that will give us 0.063. What are the units? Well, we're looking for the force, so we have, I made a mistake there, apologies. We have 0.63, sorry, year 11, 0.63 newtons. Okay, if you got 630, you forgot to do the conversion. So please watch out. This is a typical little thing that the exam board do. Even for higher papers, many students still overlook that and they make mistakes. Question 3 then, let's have a look at question 3. Here we have, again, F equals ma. Oops. M times a. Question 3. Again, we check our units. 308 kilograms is good. Now, look at this. We've got kilometers. Kilometers. We need to know that 1 kilometer equals 1,000 meters. We just need to know what that word kilo, that prefix kilo means. 1,000. So this is 1,000 times 0.56. Again, this is something that many students overlook and they just go straight into the calculation. This is actually 560 meters per second squared. Now we're ready to do our calculation. We feed those numbers in. The mass is 308 kilograms. That's good. That's the correct unit. We multiply this by 560, and already this is going to be a huge number. This is going to be a massive force required for this. 172,480 newtons of force. And again, that makes sense. We've got a large, massive object, and it's accelerating massively. Every second, it's accelerating by 560 meters per second. I mean, this is incredible, but it's going to need a huge force, and this is a huge force. Next, question 5. Again, we always start with our equation, F equals m times a, or F equals ma. We're going to rearrange, so we end up, well, we want the mass. So the mass is going to be the force divided by the acceleration. We check those units, newtons, meters per second squared. Yeah, all good, ready to go. 75 divided by 2.4, which equals 31.25. Check our units. Mass is measured in kilograms, 31.25 kilograms. Next, number 6. Again, we start with our equation, F equals ma. We are asked this time to work out the mass. So again, the mass, we rearrange this equation. The mass is force divided by the acceleration. We check our units. Well, these numbers are quite, well, one's quite large, one's quite small, but the units are correct. If the units are correct, we don't need to worry about the numbers. We just do the calculation. 5,000 newtons, so a large force to produce quite a small acceleration. So 5,000 divided by 0.6, 8333.3. Again, we're measuring the mass, or we're calculating the mass, so we have our unit. And last two. Number 8, again, F equals ma. This time we're asked for the acceleration. We're going to check first, however, that we have the right units, and we do. Newtons and kilograms. So again, we are going to rearrange this. The acceleration produced by this force working on this mass. So we have a force of 960 divided by 21. That will produce an acceleration of 45.7. Again, units, meters per second squared. 45.7 meters per second squared. That's to one decimal place. Finally, number 9. Again, we start with our equation, F equals ma. We're going to check our units. That's fine. This one, 76 kilograms. 76 kilograms. That's not right. Well, it's not the right units. So, actually, I beg your pardon, it is the right units. Sorry. 0.4 newtons and 76 kilograms. They're both correct. Sorry. The acceleration is the force divided by the mass. Therefore, just plug these numbers in. The units are correct. 0.4 divided by 76. This is about the size of a man, an adult man or adult woman. We're applying a small force. We're not expecting much acceleration. If we feed those numbers into our calculator, we end up with 0.0053 meters per second squared. So a very small acceleration, as you would expect for these numbers. Okay, excellent. If you got all those right, fantastic. If you didn't, go back and review what I've been talking about, in particular checking those units if we need to work out those prefixes. For now though, today we've been looking at something called Newton's second law, which looks at the relationship between force and acceleration, and what happens when a resultant force acts on an object. We can then use that equation for Newton's second law of motion to describe the force, the acceleration, or the mass of an object. Thank you, Year 11.